Oh, you made it! How wonderful. I'm about to talk about Jupiter and its many, many wonderful features, so come sit down and join me. Good morning, good evening, or good wherever you are, whatever time. It has been way too long since my Mars sock, but finally we're here with Jupiter. Today we'll be finishing my wonderful Jupiter socks and we'll be talking about gas giants, Jupiter's size, and general statistics. We'll also be talking about the wonderful and amazingly complex atmosphere, its beautiful stripes, and the gorgeous northern lights, which have been a rather recent discovery. We're also going to be talking about the Great Red Spot, some other storms, and of course the new images from James Webb. I'll be using red sheer 4-ply. It's the cotton colour Tutti Frutti 2. It's got passion fruits on, and you can quite clearly see that passion fruits were the inspiration for the colours here, but we'll just pretend it's Jupiter. Unlike other socks that I'm making, this one is actually made out of cotton, which I really don't like for reasons I won't get into, but unfortunately I was struggling to find a colour that was uniquely Jupiter and not like the other planets like Venus and Saturn, which we'll be doing later. Some of you were wondering, I'm using this pattern as a sort of guideline. It's this free pattern from King Cole. I was gifted it by my local craft store because they're really nice, and I've been using it as a base, although technically you don't really need to use patterns for socks because they're just more mathematically just basically calculations essentially. But if you need a pattern, I would highly recommend the King Cole ones because it has quite a few wonderful designs for you to use. Right, let's get into it. Jupiter is the largest of all solar system planets with a radius of almost 70,000 kilometers. To put that into context, Earth is around 1/10 of that, and when you plug it into the formula for volume, it makes Jupiter about 1.3 thousand times, yes, 1.3 thousand times larger, which is a huge amount. Jupiter orbits fairly circularly with an orbit of around 11.8 Earth years, making one Jovian year. So, but despite that, a sidereal day is actually really short. In fact, it's one of the shortest in the solar system, with about 9 hours and 50 minutes, which makes it probably one of the quickest rotating planets in the solar system, not including dwarf planets, I think. This is rather peculiar, and you'll actually find that following from Jupiter, Saturn has the second quickest rotation, followed by then Neptune, then Uranus, and I think you can sort of see a pattern here. So the keen minds among you may have realised I've excluded Haumea and Ceres from this, not just because they're dwarf planets, I'm not discriminatory like that. The reason being is that these orbits were probably affected by external events in the past, and so it wasn't a natural growth towards this sort of rotation. And so the likely reason that these planets seem to have shorter days is probably due to angular momentum. You see, unlike the terrestrials, the gas giants actually had a huge abundance of hydrogen and helium surrounding them during their creation, and this was a huge game changer, which we'll discuss in a bit. As these materials were pulled into the planets, it would have also increased the rotation of the planets. So it's like if you're in a spinny chair and you have your limbs stretched out and then you pull them in, you'll start to speed up. Or how when a ballerina pulls in her limbs when she does a fouette or a pirouette, she will also speed up her rotation. The reason for this is your angular momentum, and which is defined as such. So, and it must stay conserved, very similar to linear momentum, which you may have studied in school. So what happens is when you decrease this moment of inertia, this term which is denoted by an I here, when you pull in, your angular velocity will then go up in order to conserve the momentum. This is a very simple explanation, obviously, but it does, in basic terms, explain the gas giant's rotation. Before we move on to the next part, which is the structure of Jupiter, I'm just going to quickly explain what I'm doing because I realised I haven't done that, so forgive me for that. So essentially what I'm doing now is I finished the cuff, the heel, the turn heel, the actual foot itself, and what I'm doing now is I'm starting to do the decreases, very similar to the Mars sock. This is essentially so that I can actually finish it whilst I'm videoing and actually show you the socks. But yeah, so when you start the decreases, you'll alternate the decreases with each row so that it's a very slow sort of decrease into the toe, and then once you get to the end you start to ramp up that decrease rate and double it essentially so that it curves in quite dramatically into that nice curved toe shape. Now let's focus on Jupiter's actual structure. Unfortunately, we don't know as much about gas giants as terrestrial planets. Of course, they're quite covered up, especially the core. So some of this is theory, not completely proven, although there is sort of evidence for these what I'm about to say. I do, and I will try and be as clear about this as possible. We expect a fairly dense hydrogen core with helium and some other rocky materials, although there is a fairly high chance that actually some of these materials have actually been carried away from the centre, meaning that the core has sort of just disappeared. Most of Jupiter is metallic hydrogen with a small amount of helium, neon, and some other elements and materials in the lower regions. The upper layer is theorized to actually have an abundance of carbon, specifically in the form of diamond crystals, which is quite rare and unique. At the top is the atmosphere, which is almost certainly mostly made of just hydrogen. The pressure and temperature of the atmosphere is actually interesting in that it's high enough that there's no really distinct liquid and gas phase change. Now, we don't actually know how the planets formed, full stop, so I can't really tell you how these cores of these planets came to be and how they migrated around the solar system, which we know they probably did, but we just don't know how. I can tell you for some certainty about the atmosphere, however. Like we discussed, Jupiter and of course Saturn had a huge abundance of hydrogen and helium around them to pull in and accumulate. And so as they would have done, they would have increased their own mass and therefore their gravitational attraction. And so therefore they would also pull in even more hydrogen and helium, creating essentially like a positive feedback loop. And so eventually the hydrogen would become the dominant substance within Jupiter, and of course Saturn, followed by helium, giving Jupiter and Saturn the title of gas giant and thus differentiating them from the terrestrials and from the ice giants. The atmosphere is pretty much the main beauty about Jupiter, let's not lie about that. And the feature that I've decided to represent in my socks is the beautiful stripes. Well, I'm not gonna lie, all sock yarn is pretty much stripy. It's an intrinsic feature about knitting a tube, but let's just pretend that I thought about it very deeply. These stripes have been a huge mystery. Ever since we built really good telescopes, it has been just a very confusing topic, so let's actually start off with the basics. The stripes are not actually called that, they're professionally called bands. The light ones are called zones specifically. There are 7 of them, with the big one in the middle being called EZ, which is quite funny. The darker ones are called belts. There are 6 of them, plus the 2 ones at the poles. Both types of bands circulate around the planet, but sometimes in different directions, which causes quite a lot of storms in the sort of the boundary between them, which is really cool. The zones and belts stay very distinct and separate, supposedly by the jets which occur between them, which reach over 360 kilometers per hour, which is immensely speedy. These jets move in different directions, moving away from the equator, depending on whether the boundary between them is a zone then a belt, or a belt then a zone. The best example is probably the belt just above the Great Red Spot, which in itself is incredibly faster than the bands. I mean, that is just ridiculous. So what's the difference between a zone and a belt, really?
Good question!
In zones, there's a very high concentration of ammonia ice in the top layers of the atmosphere, ammonia being a very light coloured compound. Belts, on the other hand, are less dense in ammonia, and the belt clouds are actually quite thin and tend to sit closer to the surface of Jupiter. This makes the belt look a slightly darker shade than the zone, and this is actually corroborated very well with the new James Webb images, but we're going to focus on that in a little bit later. As for the differing colour, there is a theory that the compounds in the belts are a stronger orangey brown from exposure to UV light. These compounds, probably hydrocarbons or even sulfur or phosphorus, are called chromophores in this case, and they're present in both belts and zones, but also in leaves on Earth, which is quite amazing. And so what we believe actually is happening is that that high density of ammonia ice in the top layer of the zones is actually masking that darker colour. If you're a student with an Edu or an AC email, or you have some money to spare, I would highly recommend actually reading the paper itself. I'll link it down below. Although, with that being said, we have little to pretty much no clue how these magnificently stripy structures came to be in the first place. There is one idea that the distinction came from something called upwelling and downwelling, which we actually see in our own oceans. So now that we've talked about the core and the atmosphere, let's actually go one step higher and talk about the northern lights. And yes, that's right, Jupiter has its own northern lights, which is absolutely amazing, except for the fact they're in the X-ray, so you can't see them. Here's a composite image which actually has the northern lights on it. It was actually partly created by one of my lecturers, Dr. Johnny Nichols. He's a fantastic man and a great lecturer, and I was so upset that I didn't have him for second year. I mean, you know you're a good lecturer when your student actually watches the lectures for fun during lunch. So back to the topic itself. You would be correct in saying that Jupiter's lights work very similarly to ours. So charged particles zoom into Jupiter's atmosphere and interact with the gas particles that make up the actual atmosphere itself. However, one thing that we didn't know up until now is the actual origin of these charged particles. What's the key here? Jupiter's magnetic field rotates with the planet, so as the solar wind hits the planet itself, it heats up the trapped particles that are trapped within the magnetic field itself and makes them oscillate along the field lines. So this is something quite complex called, oh dear, electromagnetic ion cyclotron waves. I think that's it. But this is actually backed by the fact that the X-ray aurora is actually in sync with the oscillation of the magnetic field. It's these heated particles that go on to make the aurora borealis, but we don't know where they came from until very recently. Jupiter's aurorae happen all the time, every 27 minutes to be precise, so it needs a very constant supply of particles. Scientists have actually confirmed that it is actually made up of oxygen and sulfur mainly, which are supplied by our astronomers' favourite moon, Io. This moon is actually one of the most volcanic surfaces in the solar system, and it provides a huge supply of gas. So Io supplies oxygen and sulfur to the magnetic field. The solar wind then heats up these trapped particles and then makes them oscillate, creating those EMIC waves. These particles then collide and create the X-ray aurora. So the discovery itself was made by the Chinese Academy of Sciences, with a special mention to Zhonghua Yao and his colleagues, plus Dr. Dunn from UCL. You can find the paper which basically outlines this theory and the evidence and amazing discovery below. Now let's talk about the astronomers' favourite storm, the Great Red Spot. I think I'm on my last few rows here, so we're almost done. The Great Red Spot has been a massive interest for centuries now. It's an anticyclonic storm, meaning in this case it rotates anti-clockwise, and it's about 16,000 kilometers wide, which is way bigger than Earth. Earth's diameter is about 13,000 kilometers if I remember, so it's about 1.3 times larger. The Great Red Spot has actually been observed since 1830, but it's likely that it existed since, I think, the 17th century, which is very old. We have no clue really how this storm was created, but thanks to a lot of recent observations, we've built up a huge amount of knowledge about the Great Red Spot. Another storm that's less mentioned, but just as amazing in my opinion, is Red Spot Junior, essentially the oval BA that we mentioned before. It was first discovered at around 2000, but we know that it's actually the product of 3 storms that have merged together. Okay, hear me out. There's also another red spot that we call Baby Red Spot, or the South Tropical Little Spot in more professional terms. This one was actually destroyed and eaten by the Great Red Spot in 2008, so rest in peace, little dude. And finally, I think we should have a look at the new James Webb images. This image is an infrared image with false colouring to differentiate between wavelengths of light. You can see a huge amount of detail such as storms, hazes, and even the aurora itself. So this is actually a composite image, made of data taken from 3 filters on the near-infrared cam aboard the telescope. The red coloured comes from the filter for the longest wavelengths, the middle wavelengths are represented from the yellow filter, and the shorter wavelengths are from the cyan filter. It's sort of essentially taking human vision and sort of shifting it into the infrared. Here is an even bigger image, including the moons and the rings. And this one's actually only made up of 2 filters, an orange filter and a cyan filter. The little white dot on the left is actually the moon Amalthea. The moon at the leftmost point of the dusty ring is Adrastea, and the straight lines at the north and south pole are diffraction spikes. What's interesting about these images is how bright the EZ band is, and the great red spot especially, although it's not very red here obviously. Given from the previous theories that we discussed before, the EZ band and the great red spot are actually at very high altitudes, and so their cloud cover reflects sunlight and hence infrared very well. So I'm on the final row here, I'm just doing all the decreases. I'll then sew up the toe of the sock and we'll be done. I would highly recommend that you actually read up on these images a little bit more on the James Webb and the NASA.gov website. There's a lot more detail on them there, and you can download some really high quality pictures of them. Okay, so I'm just finishing up the toe. What I'm doing is I've got a metal needle over here, a sewing needle that is, not a knitting one, and I'm just moving the end of the yarn through all of the stitches just to catch them all, and then I'll just tie a knot and sort of secure it. So yep, all of these stitches have been caught, you just pull it tight, and then you will secure this by, I personally just go through another round and then I'll just weave in the ends. There we go. Okay, all done. So let's check. Yep, that's all done. So there we have one beautiful Jupiter sock. Oh, there we go. Wonderful. It's really nice. I really like the colours. The yellow is definitely not quite as astronomically accurate, but you know, we'll just let it slide. And with that, I've actually now got 2 beautiful Jupiter socks that I can wear and show off. There we go. There is one gorgeous Jupiter sock. Okay, so now that the socks are all done and I've pretty much spoken about as much as I can about Jupiter, I think that concludes this video very well. Oh, also, I have some really good news, and that is I'm back on the master's course as well, so I'm really happy about that. With that being said, thank you very much for joining me. I hope you learned something new, or that I was a good knitting companion if you were knitting along with me. With that being said, my next video, I'm not sure what it'll be on. It might not be on Saturn just yet. So thank you very much for joining me. I'll see you soon. Bye.